Okay, in this flip lesson, we are going to focus in on the second subtopic in the motion, forces, energy, and momentum topic, and that is forces. We're really going to focus in on Newton's laws of motion. Hopefully, you've all looked at those before in previous years, so a lot of this will be a little bit of a recap. Maybe we'll take it to a slightly higher level this year. Cheers. Okay, to start with, we are going to look at what a force is and how it affects the motion of an object. Really going back to what you probably did in middle school. Then we're going to look at Newton's first law and the concept of inertia. And then finally, which I'll do on the next slide, we're going to describe and explain the motion of an object falling in uniform gravitational field with air resistance. And we're really going to look at the concept there of terminal velocity, and I'll do that on the next slide. So firstly, a force can be a push or a pull. You might have also learnt in middle school that a force could be a twist, but to me, a twist is just a combination of a push and a pull. You push with one and pull with the other, and that creates a twist. So really simple picture in your head of what's a force is it's a push or a pull. Force is measured in newtons after Sir Isaac Newton and has the symbol N. A force will cause the motion of an object to change, i.e. it'll either speed up, slow down, or change direction. And all of those things we regard as an acceleration. Remember, an acceleration is a change in velocity. So obviously, if something speeds up or slows down, the speed is changing, the velocity is changing, so it's an acceleration. But, and this will become important particularly next year, if an object purely just changes direction, then it is also accelerating because velocity is a vector. Vectors have a direction. If the direction changes, therefore the velocity is changing, so it's an acceleration. Then we get into Newton's first law. If the body is at rest, it will remain at rest. If the body is moving at constant velocity, it will continue to do so unless acted upon by an unbalanced force. And the classic example that you've probably talked about, it was probably, why we wear seatbelts or something like that. But we can see Fred driving along in his car here and he slams on the brake to not hit this dog. And the golf clubs aren't strapped in and they all just keep going at constant velocity. So, obviously, I think the first part, if a body is at rest, will remain at rest, is pretty obvious. Things don't just suddenly start moving generally. If the body is moving at constant velocity, it will continue to do so unless acted upon by an unbalanced force. I think by this level most people understand this, but sometimes people think inherently that all objects, if you just leave them going, will slow down. Now, in reality of our world, they will slow down because friction will act. That friction could be friction due to collisions with air particles, which is what we know as air resistance, or it just could be friction with a surface. So that friction provides a force that causes the object to slow down. But if we were to go deep into space where there was no air molecules and we were to send an object moving at constant velocity, it will keep going at that velocity forever. It won't slow down. Its tendency is to keep moving at a constant velocity. And we call the tendency for an object to keep moving at a constant velocity inertia. So basically, when we talk about an object having inertia, that is the concept that the object wants to keep moving at a constant velocity. You can think about standing on a train here. This cartoon shows standing on a train, which shows a good little thought experiment for that. If you're standing up on a train, stationary train, you're standing there, no problems, everything is balanced. If that train accelerates, so that train speeds up, your body, still here at rest, its tendency is to want to stay at rest. That means it wants to stay in the same position. So as the train accelerates forward, your body wants to stay in that position so it feels like you fall backwards. But you're not actually falling backwards, you're just trying to stay in the same position as the train moves forward with respect to you. Then, when the train tries to come to a stop or decelerate, your body is moving now at constant velocity. As the train slows down, your body wants to keep going at constant velocity. So what happens is you tend to move forward with respect to the train. So you want to keep going at the constant velocity. The velocity of the train is decreasing, so your body tries to keep going, and that's why you would lurch forward. So that is Newton's third law, and we've looked at a couple of contexts there. And then in the next slide, I just want a bit more space, we will look at this concept of air resistance and gravity and terminal velocity. So let's consider a skydiver, and they've just jumped out of a plane. And initially, the main force that's going to act on them will be gravity. And that force will act downwards, like so. And at least in that initial situation, that force is going to cause an acceleration of 9.8 meters per second. And in that initial situation, that'll essentially be the only force acting on them. Now, gravity acts at a constant rate. The acceleration due to gravity is 9.8 meters per second. So the force due to gravity will not change as they fall towards the Earth. But a force is being applied, so when a force is applied, it changes the motion. It'll cause an acceleration, and in this case, it will continue to cause the person to accelerate towards the ground. So even as they speed up, the force due to gravity will still be the same. And we can represent that with basically this vector. And we represent a vector with an arrow where the direction of the arrow indicates the direction of the force, which is downwards, and the size of the arrow indicates the magnitude of the force. And I've just realised I've probably made those. Yeah, those two arrows are supposed to be the same. The force due to gravity does not change. But what you do, you might have done this experiment before, but otherwise think of it like a little thought experiment. If you're driving along, if you're standing in your car and you put your hand, if you're sitting in a car that's not moving and you put your hand out the window, you won't experience any force due to air resistance on your hand if you're not moving. However, as that car speeds up, the air will push back on your hand. So if you're driving along at 110 kilometres an hour and you put your hand out the window, you'll feel a real force pushing on your hand. And that's the air pushing on your hand. So what happens with that? This skydiver who's falling towards Earth is they will speed up. And eventually when they hit about 200 kilometres an hour, which is about just roughly 60 metres per second, the force due to the air resistance as they fall at that speed will be equal to the force due to gravity. So at this point, the person will no longer accelerate. The force due to gravity will be acting downwards. There will be an equal force in the opposite direction acting due to air resistance. So the net force on the person will be zero. Now, that doesn't mean they stop. A net force of zero doesn't mean they stop. A net force of zero means they just keep going at a constant velocity, what we just talked about with Newton's second law. So in between these two states, that gravity line will stay constant, and as the velocity increases, the air resistance will increase until you get to a point where the force due to gravity is equal to the force due to the air resistance, but in the opposite direction, or the air resistance force is in the opposite direction, and they'll reach a terminal velocity. You may have or may not have heard me tell the story. this is a sort of good news, bad news story. If you ever fall out of an aeroplane without a parachute, the good news is that you will live longer than you would predict just from those equations of motion that we discussed in the last in the motion part of this topic, because you won't your velocity won't keep increasing and increasing and increasing and increasing, and by your velocity getting faster and faster and faster, your time until you hit the ground will decrease and decrease. Well, yeah, it will be decreased compared to what it would be if you were moving at constant velocity, because you continue to accelerate. So the good news is you'll live longer than you might think, purely based on using the equations of motion that we discussed in the motion subtopic. However, the bad news is when you hit the ground at about 200 kilometers an hour, you're still going to die. So you get to live a little bit longer than maybe Newton's equations of motion predict, but you still will die. So hopefully I have made that clear. So now let's talk about Newton's second law. When an unbalanced force acts on a body, it produces an acceleration in the direction of the force. The acceleration is directly proportional to the applied force and inversely proportional to the mass of the body. So, if we think about a skydiver from the previous slide, that initial case, gravity is an unbalanced force. Gravity acts on the force. It causes an acceleration in the direction of the force, which is towards the ground, so the object will speed up towards the ground. If you've got a book sitting on a table, if you push on that book will move, will start to move, so it will accelerate in the direction that you apply the push, you apply the force. Hopefully that's pretty self-explanatory. That's, if you like, the first sentence there. The second sentence, the acceleration is directly proportional to the applied force and inversely proportional to the mass of the body. And if we get a chance, we'll look at this in the lab, but again, I think it's fairly self-explanatory. The greater the force, the greater the acceleration. The harder you push something, the faster it will accelerate, or the more it will accelerate. The greater the mass, the less the acceleration. So if you push it takes a lot more force to accelerate a truck than it does a car. It takes a lot more acceleration to push to accelerate a heavy object than it does a lighter object. So mathematically, we can say that acceleration is proportional to the force. So as the force gets bigger, the acceleration gets bigger. So that is the numerator in our equation. And as the mass gets bigger, the acceleration gets smaller. So the mass here is the denominator. As this number gets bigger, this number will get smaller. More commonly, we see it written in this rearranged form, which is F equals ma, or we might put force equals m multiplied by a. We don't have to put this multiplication symbol in. In physics, you can see how it's written up here. We accept that if there's nothing written between two things, that's a multiplication. The units for force, already talked about before, are newtons, and a newton is 1 kilogram per meter per second to the minus 2. So mass is in kilograms, acceleration is in meters per second to the minus 2. If you want to get a feel for what 1 newton feels like, if you get those masses, those slot masses that we often use in the lab, they weigh 50 grams each. So if you get 2 of them, you'd have a mass of 100 grams. 100 grams is 0.1 kilograms. Just divide by 1,000 to convert grams to kilograms. And the acceleration due to gravity is 9.8 meters per second per second. So if they're held up above the ground, they will accelerate at 9.8 meters per second per second. Due to gravity, the force that they would exert on an object, if you're holding them up, would be equal to mass times acceleration, which is obviously equal to, just grab my pen, 0.9 1 times 9.8, which is equal to 0.98 newtons, which is basically approximately 1 newton. So if you just want to have a feel for what does 1 newton feel like, it's holding 100 grams in your hand. It's roughly basically like, I think holding an apple, something like that. No, apple's probably closer to 200 grams. You'd have to get a fairly small apple to probably get 100 grams. Okay, there's another important thing we need to talk about here, and that is to explain the difference between mass and weight. Now, in everyday life, we use mass and weight interchangeably. So, how much do you weigh? What's your weight? What's your mass? But strictly speaking, in physics, mass is a measure of the amount of matter in an object, and it's measured in kilograms. Weight in physics is the force you exert on the ground due to your mass and gravity measured in newtons. So let's do a little thought experiment here. If you're standing on the earth and you weigh 50 kilograms and the acceleration due to gravity at the earth is 9.8 meters per second, your weight will be equal to the mass times acceleration, which will be equal to 50 times 9.8, which will be equal to, if I have this correct in my head, 490 newtons. So, if you weigh 50 kilograms, 490. You can approximate the 9.8 to 10. So, it's just under 500 newtons would be your weight. That would be the force you exert on the ground due to your mass. However, if you went to the moon, on the moon, the acceleration due to gravity is only 1.62 meters per second. And what that would mean is that when we work out our weight, which is that force on the ground, it would be 50 times 1.62, which would equal, if my mass is correct here, 81. I haven't grabbed a calculator, so I hope I have got that right. 81 newtons. So that is the difference between mass and weight. And I know in everyday life we tend to use them interchangeably, but in physics they do have a separate meaning, and you need to be aware of that. The other thing we need to do here is undertake experiments to investigate the relationship between acceleration and either force or mass, and if we get a chance, we'll do some of that in the laboratory. So let's look at Newton's third law. Whenever one object exerts an action force on a second object, the second object exerts an equal and opposite reaction force on the first. The classic example to demonstrate this is why you get recoil when you fire a gun. The action force is the action of the gases and the bullet being forced out of the end of the barrel. That reaction force is that the projectile as it's launched, there's an equal and opposite reaction force on the gun, so the gun basically recoils or is accelerated backwards, creating that recoil. There is some really funny recoil videos on YouTube. They're not as easy to find as they used to be, but Americans firing gun fails, something like that on YouTube, you see some really good examples of people not properly understanding Newton's third law. So let's just look at a couple of common contexts. And again, you've probably seen these in middle school. We might expand that a little bit. Of basically our force pairs. So let's say here we've got a rocket being launched. The action force is the action of the fuel, the hot gas, being expelled out of the rocket The reaction force is the rocket will accelerate in the opposite direction to the direction that the fuel is being fired out the back. If we think about a car moving along a road, the action force, if you think about the wheels on the car at the bottom are spinning that way to make the car go forward. So the action force here is from friction between the tyres and the road, and the reaction force will be equal in size in the opposite direction, and that will be what causes the car to accelerate forwards. If we look at the hammer and the nail here, if we hit a nail with a hammer, we know the hammer doesn't keep going at constant velocity. The hammer slows down after it makes contact with the nail, so obviously a force has been exerted. So if you like, our action force here is the hammer hitting the nail, and the reaction force is that the nail exerts an equal and opposite force on the hammer that causes the hammer to slow down. If we're here rowing in a boat, the action force is the oars sweeping backwards, pushing the water backwards, and the reaction force is the force that accelerates the boat forward as you row. Now, the other context that we need to talk about here is the normal force. The normal force, normal in mathematics, so normal is a perpendicular line, and in a sense, if we have an object or if we are standing on the ground, the action force here is gravity. That's pushing us towards the ground. The ground exerts an equal and opposite force on us in an upward direction that's called the normal force. In this scenario, I think that's pretty easy to picture. But if we are on a sloped angle, the normal force is always perpendicular to the ground. So that normal force will always act perpendicular to the ground. Next year, we're going to see how this is important for things like banking angle on velodromes, if you've been watching the Olympics, or on even designing roads and all sorts of things. The fact that this reaction force here, the normal force, always acts at 90 degrees to the surface, so the reaction force to gravity is the normal force, does have some interesting applications that we will explore next year. But for now, normal force is just that equal and opposite force due to gravity, but it always is exerted at 90 degrees to the surface of the ground. So I think Newton's third law to solve problems, well, we've talked about how we sort of interpret that, and then we would apply that using Newton's first and second laws or the equations of motion, which we've already done. We've identified force pairs, including the normal reaction. We've described and explained motion, where third law occurs. All of these examples relate to that. Use Newton's laws to explain the motion of spacecraft. That basically is this idea here of the gas being expelled out the back, which causes a reaction force which accelerates the rocket. So hopefully that has covered Newton's laws in sufficient detail for you this year. Cheers.